Hello, everyone, and welcome to Signal Systems and Signal Processing with Wolfram U. The topic of this lesson is Fourier transform. Previously, we defined Fourier series as a representation for well-behaved periodic signals. In this lesson, we turn our attention to non-periodic or aperiodic signals. We will see that such signals, under certain conditions, have a representation that we call the Fourier transform. The Fourier transform can be viewed as a natural extension of the Fourier series, simply by considering aperiodic signals as periodic with their period extending all the way to infinity. Looking at the line spectrum of a square wave signal as an example of periodic signals, you can see that the line spectrum gets denser as the period gets larger. It seems reasonable to imagine that as the period goes to infinity, the line spectrum, which is a discrete function of frequency, transforms into a continuum. The continuous time Fourier transform, or Fourier spectrum of a signal x of t, denoted by x of j omega, is defined by the integral shown here. This formula is known as the Fourier transform analysis formula. The synthesis formula can be used to obtain x of t given that we have its Fourier transform x of j omega. Similar to the conditions for existence of Fourier series, the Fourier transform of a signal x of t exists if the signal has finite energy as indicated here. This means that all bounded and finite duration signals have Fourier transform. Also, the following conditions, known as Dirichlet conditions, are sufficient conditions for existence of Fourier transform. On any finite interval, x of t should be bounded and have a finite number of maxima and minima and a finite number of discontinuities, and it should be absolutely integrable as indicated here. Let's find the Fourier transform of the unit pulse signal as defined here. First, we can check whether the Fourier transform exists by testing the absolute integrability condition. Using the Wolfram language, taking the integral, we get 1, so the Fourier transform does exist. And we can also use the Wolfram language to find the Fourier transform, which gives us sinc omega over 2. Plotting the Fourier transform for the signal x of t, we can see how it changes for different values of omega. Now, if we were to use the analysis formula to find the Fourier transform, we substitute x of t with its value and find the integral and simplify the results. We get the same sinc function for the Fourier transform. Let's look at another example and find the Fourier transform of the exponential function x of t defined as shown here. We can easily check again and see that the Fourier transform exists and also find it using the Wolfram language. Now again, to obtain the Fourier transform using the analysis formula, we replace x of t with its value, combine the two exponential terms here into one, evaluate the integral, and simplify the results. Since the Fourier transform is a complex value, we usually plot the magnitude and phase of the Fourier transform, or sometimes the real and imaginary parts. You can see how these values change over frequency. Also, as you can see, in both cases, the Fourier transform is symmetric, and for this reason, it is common for the Fourier transform of a real signal to be plotted over just the positive values of frequency. It is also very common to plot the magnitude of the Fourier transform using a logarithmic or decibel scale, as we have here. If we also use the logarithmic scale for the frequency axis, we get what is called the Bode plot of the transfer function. As we mentioned before, if the Fourier transform of a signal x of t, x of j omega, is known, we can obtain the signal itself using the synthesis formula. For the exponential example, we found the Fourier transform. Now, if we want to find the signal itself using the Fourier transform, we can apply the function inverse Fourier transform to find the original signal xft. Let's look at another example and find the inverse Fourier transform given the Fourier transform shown here as a unit box. Again, using the Wolfram language, the signal is found to be a scaled sinc function. As usual, we can plot the signal to see how it changes over time. Now, using the synthesis formula, if we replace x of j omega with its value, evaluate the integral, and simplify further using the Euler identity here, we get the sine of t over pi t, which is the same sinc function that we obtained earlier. For any given signal, if we can identify a range of frequencies where the signal's magnitude is relatively large, that range of frequency is what we define as the bandwidth of the signal. As an example, consider these four pulse-shaped signals. If we find their Fourier transform and plot their magnitude spectra, we see that the spectrum of the square pulse, which is the sharpest signal of the four shown here in blue, drops off the slowest compared to the others as the frequency increases. So the square pulse, we say, has the widest bandwidth. This concept of bandwidth for a signal is important when we consider the transmission of the signal through some bandwidth-limited media. Periodic signals have Fourier transforms, but if we try to evaluate the integral in the existence condition for the Fourier transform, for example, for a sinusoid here, we see that it does not converge. For periodic functions, we can, however, indirectly obtain the Fourier transform using their Fourier series. To see how, let's get the inverse Fourier transform of an impulse function, as shown here. We get a complex exponential signal. So we have this relationship between a complex exponential in time and an impulse function in frequency. For any periodic signal x of t now, if we consider its Fourier series representation, which is a series of complex exponentials as shown here, and take its Fourier transform, we have this expression shown here using the relationship that we just found. This is the Fourier transform of the periodic signal x of t. What we have is a superposition of impulses scaled by the Fourier series coefficients of the signal. They're located at the harmonic frequencies of the signal or the integer multiples of the fundamental frequency. As an example of a periodic signal, consider the square wave shown here, and let's find its Fourier transform. First, using the Wolfram language, we can find the Fourier series coefficients. Note that the period of the signal is 1. Equivalently, the Fourier series coefficients are given as indicated here for all values of k. And so the Fourier transform using these Fourier series coefficients can be found by replacing ck with this value. Let's plot the Fourier transform and see how it changes over frequency. We have this series of impulses. In this lesson, we learned about the Fourier transform. We went over several examples where we found the Fourier and the inverse Fourier transform. We compared the bandwidth of several pulse-shaped signals. And we also derived the Fourier transform of periodic signals in terms of scaled and shifted Dirac delta functions.